Hello everyone, I'm J Wildberger, and welcome to this famous math problem where we're going to investigate how to set up a proper theory of infinitesimals. Very important notion for calculus and analysis that's actually been hugely contentious over many centuries, in fact even millennia. So according to Wikipedia, an infinitesimal is a number or quantity that's closer to zero than any standard rational number, but is not actually zero. And somehow we visualize these strange creatures, sort of be on the number line. There's the number line, 0, 1, 2. Rational numbers, say half, a third, minus a half. Where are the infinitesimals in this picture? They are really close to zero. Really, really close to zero, but not quite zero. So they're so close to zero that they're smaller than any other positive rational number that you could define. They're smaller than 1 over a million. They're smaller than 1 over a billion. They're smaller than 1 over a trillion, etc. But they're not zero. Okay, so this concept, even though it's obviously sort of strange arithmetically, it's actually very historically important and plays a foundational role in calculus and also a very useful role in physics and engineering. But there is a natural question with this, of course. The question is, what is an infinitesimal exactly? So in this famous math problem, we're going to frame it this way. The problem is how to develop a proper theory of infinitesimals. And I rate this at a difficulty level somewhere between 4 and 8. In some sense, it's a solved problem. So I'm going to show you something that's known, okay, even though it may not be well known. But there's also aspects of it which are, in some sense, still unsolved. So this is a strange kind of problem. So today we're going to talk about the history of the infinitesimals, a little bit about the objections that 18th century mathematicians and others centered on this concept. And we'll also briefly talk about non-standard analysis. And we're on the road to explaining proper theory of infinitesimals in the context of what we might call dual complex numbers. So this is going to take place in the algebraic context that we've just been talking about in our previous famous math problem, number 21, where we talked about constructing the true complex numbers. We saw there were 3 different kinds of complex numbers, blue, red, and green, and they all are contained in this sort of all-embracing algebra of the dihedrons, which is really just the 2x2 matrices. And that's the framework that we're going to be using, and I'm going to show you that there is actually another kind of complex number system inside the dihedrons, which is different from these 3, which we're going to call the dual complex numbers. And we denote that by a C with a little d. Okay? These are the dual complex numbers, and that is going to be the starting point of our purely algebraic, completely precise, unambiguous setup of infinitesimals. And it's going to have the remarkable aspect that it actually works over a general field, which is at first highly non-intuitive. So the story of infinitesimals goes back to the ancient Greeks, and we can identify a kind of a clear enunciation of some of the ideas in Archimedes, arguably the greatest thinker of all time. So Archimedes lived around 250 BC in Syracuse, in Italy most of the time, and he wrote many important books. But one of the most fascinating is a text called The Method of Mechanical Theorems, which was actually remarkably only discovered relatively recently. It's often called just the method. And the story of this is quite interesting. It was found almost by accident in the beginning of the 20th century, okay, where there was an ancient document of some kind and had some I think perhaps religious stuff on it, and it was being cleaned up, and people realized there was something behind the more modern works, and they were able to sort of analyze what was behind it, and they realized ultimately that this was actually a sort of a lost work of Archimedes. And it's very interesting because this document sets out Archimedes' thinking, okay, how he discovers a lot of his important results that are really precursors, really actually the first kinds of systematic results in calculus. Okay, and one of the key ideas here is that Archimedes wants to think physically. So he's aware of the idea of a lever, important principle of Archimedes, the principle of balancing of a lever. And he wants to exploit this by casting mathematical problems as physical ones and almost treating a lever like an equation with two sides of the equation and balancing what's on one side with another. So during that time, most of the standard calculus questions had something to do with areas, or in 3 dimensions with volumes. So there was a general program called Quadrature, where we try to find areas of things which don't obviously have nice formulas. And a key example is the area, say, determined by a parabola. Okay, for example, let's say y equals x squared. There's the familiar graph of that parabola, just from x equals 0 to x equals 1. And all calculus students learn that the area under this curve from 0 to 1 turns out to be 1/3. And this was something that was known to Archimedes. And we can illustrate his thinking to how to sort of establish this fact. And it's very clever. So what he does is he looks at 2 different things and he's going to balance them. Over here is the object that we're interested in, the graph y equals x squared from 0 to 1. And over here also in the xy plane is a much simpler triangle with vertex at the origin, here at the point 1, 0, and here at the point 1, 1. So this is the line y equals x. Okay, so this is a right isosceles triangle with base 1. And of course, the area of this thing is easy to determine. It's 1/2 base times height, so the area is 1/2. And Archimedes is thinking in terms of subdividing this 2-dimensional region into a bunch of 1-dimensional strips. So imagine this little line here as a kind of ingredient or constituent of this 2-dimensional area. So if this little vertical strip here is at, say, the point C in the x direction, then its height will also be c, because this is the line y equals x. Now, this c, we're going to regard this whole thing as sort of being a physical kind of thing. So we're imagining we're looking down on a piece of paper which is balanced on the y-axis. So for example, if I take, say, a book, okay, and that's like the plane, but I'm thinking of it as being positioned so that this is the y-axis. The y-axis, maybe the x-axis is here. So instead of being like this, I'm going to turn it like this. And then I'm going to try to position things so that we have balance along this y-axis. So that involves Archimedes' principle that the amount of torque or turning that a given mass has on this situation is a product of its displacement from the fulcrum times the mass. Okay, that's called the moment. So in order to calculate how much total torque this triangle contributes with regard to the fulcrum on the y-axis, we can look at these little pieces individually. And this little piece here, okay, it's going to be of distance c from the axis, and its mass is proportional to its length, so that's c. And so the moment in this case is c times c, which is c squared. Okay? So in other words, as we move this thing over, it's a quadratic dependence. The amount of torque that these little vertical pieces create is a quadratic in terms of the c. Now that means that this torque obtained from this thing here exactly matches the length of this part of the graph under y equals x squared. Here is c, then the y coordinate here is c squared. So the torque of this thing will be balanced by the length of this thing. And then what we can do is we can try to balance these things in a physical way. Okay, so here's another picture. We've copied this triangle over here. And now on the other side of the y-axis, here is our axis, which is where we're balancing things. On the other side at -1, minus 1. We are going to put this little segment here. Okay, so this segment has height c squared. So if we put it at minus 1, then its displacement is 1 in that direction, and its length is c squared. So the moment that it will create sitting above minus 1 is exactly equaling the opposite moment on the other side of this particular segment that we started with here. So what he's doing is he's stripping this area into a large number, maybe even an infinite number, of infinitesimally small strips. And he's balancing these strips on one side with portions of the area underneath here. So to create a nice balance of the whole thing, what we should do is we should put the entire area under the parabola on the point minus 1. So you can have a look at this. I'm trying to show you here on a kind of another axis. You know, we're taking the copy of this thing here and placing it maybe in this kind of direction here so that it's sitting above minus 1. Of course, we're thinking about this thing as being horizontal. So this entire area is sitting over here, and that means that all of these individual pieces here will all be of separation 1 from the axis. And so their torques or their moments will exactly equal the torques of the corresponding vertical slices of this triangle. So this is Archimedes' totally brilliant idea that we're going to match these things up so that there now is balance. Now, if you look at it from that point of view, the entire triangle over here, the entire torque of that triangle, is determined by looking at its center of mass. So Archimedes knew about that. He knew that you could easily calculate the center of mass of this triangle. It's at the point with coordinates 2/3 and 1/3. You can get that by taking the intersection of the medians, for example, or if you like, just taking the averages of the 3 vertices. So there's the center of mass, and its separation from our pivot axis is the x-coordinate, which is 2/3. And the area of this triangle, as we've said, is equal to 1/2. And so the cumulative moment of the entire triangle with respect to this horizontal axis is the product 2/3 times 1/2, which is 1/3. Now on the other side, we've put the entire parabola over here on top of minus 1. So all of those things are at distance 1 from the axis. So over here, the balancing moment is 1 times the total area under the parabola. And we've just said that these two things are going to balance in terms of the lever. And that means that the total torque here is going to be 1 times the area. It's just the area A of the region under the parabola. And from that kind of argument, he can deduce that therefore A has to be equal to 1/3. So this is a very remarkable argument, which illustrates all kinds of important things. So first of all, it illustrates the importance of physical thinking in Archimedes' time, actually just due to Archimedes, which is really some kind of anomaly in the history of analysis. So no one has, I think, really systematically taken this up in a big way and said, let's see how far we can push this kind of thing in other directions. Okay, so this is some kind of just idea that Archimedes had that hasn't really been properly developed, not really developed by subsequent analysts in the thousands of years afterwards. And of course, maybe part of the reason is because this was only discovered in the early part of the 20th century. Okay, another key aspect of this is that it's crucial that we regard these strips that we're taking as infinitesimal strips. So if you actually look at not infinite strips or infinitely small strips, but actually strips of some finite width, then the argument breaks down a little bit, because then you don't have exact rectangles here. You have rectangles with sort of triangular tops over here and rectangles over here with parabolic tops. Then it becomes, the argument becomes weaker. Okay? So the argument is simple because we're just using these infinitesimal strips. But, the question still remains, is this logically valid? To what extent can we talk about infinitesimally small strips? Now, crucially, Archimedes was aware of the logical difficulties of this kind of argument. Okay? And so what he did is he used this kind of thinking to discover theorems. For example, they discovered the formula for the volume of the sphere and the surface area of a sphere using arguments in this direction. But he proved them using a rather different technique of exhaustion, which had been developed by Eudoxus. Okay, so he had an interesting point of view here. He had this as a kind of empirical way of discovering things, yet he understood the logical subtlety and preferred to prove things using an entirely different method, where you basically sort of bound things and and have a lower bound and an upper bound, and then you kind of gradually sandwich things together to get what you want. Okay, so already in the ancient Greek times, we see infinitesimal ideas being used in a very strong way by Archimedes. Now, if we fast forward to the European era and the beginnings of calculus, we curiously see a similar kind of convergence of ideas, that the idea of infinitesimally small strips or indivisibles was being used by a number of people in the time period just before the emergence of calculus. So a prominent person here to illustrate the idea is B. Cavalieri, who lived from 1598 to 1647. And he employed this kind of thinking systematically in a lot of contexts. And I want to give you an example of his thinking. So here is a parallelogram ABCD. And this diagonal divides it into two pieces. And perhaps we're interested in proving that the two areas of the triangles here are equal. Okay, so the area of triangle ABC, this top one here, equals the area of triangle ACD. Now, his argument is nice. It doesn't really involve much geometry at all. He says, okay, suppose that we go up a certain amount in this direction, say from A to E, and we go down correspondingly a certain amount here, say from C to F. So this segment and this segment are actually equal. They're actually parallel and equal. So these are like identical vectors, if you like. Now suppose you look at this little horizontal strip that goes across the top triangle from E to, say, G. So it's parallel to the base and the top, and correspondingly this little strip here. Okay, so then he says, okay, we have parallelogram here, we have similar triangles. This triangle is similar to this one, and these sides are equal. So then these two sides are equal. We deduce that the side EG equals the side HF. And then he says, okay, that proves it, because we can think about this triangle here as just being a union of all kinds of little strips, linear strips, all parallel to this base that fill out this thing here, and this one here is correspondingly a union of such strips. And we've established the identity of these individual strips on a sort of a one-to-one basis. So he's thinking about areas of a two-dimensional region as a cumulative effect of a lot of little linear elements, sort of like this. Okay? The area here is really formed by these infinite number of indivisible little lines. So here's this idea that a line is like a whole bunch of points, like a string of pearls. And correspondingly, a two-dimensional figure like this is a family of one-dimensional, like, threads. Okay? And this was a very important thinking in his mind, and you can see that it's quite parallel to what Archimedes was thinking, although he would not have been aware of Archimedes' thinking in this direction, I'm pretty sure. Notably, Cavalieri was able to prove something much more substantial than this. So he came up with this formula here, which is arguably the most important formula in calculus in terms of a computational formula. The integral from 0 to 1 of x to the n dx is 1 over n plus 1. So in the case of n equals 2, we recover Archimedes' parabola formula, but this is more general. And he proves it for n equals 1 to 2 up to 9. And he does it with essentially geometrical arguments involving subdividing areas into lots of little like strips, and maybe moving those strips around a little bit, and then arguing that the areas are not going to be changed. Okay, so this is a geometrical kind of use of infinitesimal things, but the infinitesimal things are actually sort of one-dimensional elements. Okay, so it's powerful, it's interesting, and certainly this is a very spectacular application of Cavalieri's thinking. So around this time, there were many people thinking in roughly similar kinds of directions. We had Roberval, we had Pascal, we had Fermat. But I think sort of the role of infinitesimals really came to a head with the work of Leibniz, who was one of the founders of the modern version of calculus. Leibniz lived from 1646 to 1716, and he was maybe the supreme genius in an age of geniuses. He discovered his approach to calculus by really appreciating the parallels between essentially discrete kinds of summations and differences relations and the corresponding continuous analogs of integration and differentiation. So for example, if we start with a discrete sequence like this, say 1, 2, 3, 4, 5, very simple, then we can employ sort of summation to sum partial sums of this thing. So we start with 0, and then we get 1, and then the first sum of the first 2 terms is 3, and then the sum of the next 3 terms is 6, and then the first 4 terms is 10, and then 15, and so on. We get actually the triangular numbers. So this is a way of going from one sequence to another by summation. And the other direction, to go from here to here, is a question of taking differences. If you want to recover this one from this one, you take differences. 1 minus 0 is 1, 3 minus 1 is 2, 6 minus 3 is 3, etc. Okay? So this was a very important, motivating insight of Leibniz, and he saw that integration was very parallel to this. Okay? And to make the parallel as close as possible, he drew upon infinitesimal ideas. He really tried to think about an area like this as being almost a discrete version of many, many small little contributions. So in some sense, perhaps an infinite number of infinitely small contributions. Okay? That was pretty close to the way he thought. So for example, if you say we're interested in the area under y equals x, which is some kind of continuous analog of this sequence, then let's say you go over to the point x and you say, okay, what's the area of that thing there? Well, you can calculate the area just like we were talking about in the previous example. It's a quadratic thing. In fact, it will be x times x over 2, so it'll be x squared over 2. So over here is the graph of the cumulative areas that you get under this linear curve. You get this quadratic curve, y equals x squared over 2. Okay, so that's how you go from integrating this to this thing here. And then he realized that the inverse operation, to go backwards from here to here, was a continuous analog of the difference operator here. And that continuous analog involved taking differences, okay, but very, very small differences, which effectively ends up essentially being differentiation, okay? And he did many things. He contributed the modern terminology. So basically, the modern terminology of calculus, which has been around for hundreds of years, was basically invented directly by Leibniz and has basically not been adjusted very much at all. It's really quite remarkable that his insight was so good that he came up with this really great notation. So he thought in terms of infinitesimals. So to do an integration like this, he had the notation like this: the integral from 0 to t of f of x dx. This dx represented some infinitesimal small width. And this f of x represented the height, and this was the infinitesimal area of this infinitesimal rectangle, and this integral was basically a summation. So it was notation that sort of paralleled what's going on in the discrete case. And going backwards, we have the derivative, which is sort of a ratio of the change in f over the change in x. So again, he employs this infinitesimal kind of notation where df represents some infinitesimal change in f and dx represents some infinitesimal change in x, and this ratio here corresponds to the slope of the tangent. Okay, so he's very much using infinitesimal ideas to set up his calculus, and this was hugely influential. So Leibniz thought in terms of variables and their changes. So the differential dy of a variable y was to him a very small but non-zero change in y. Okay? And he recognized that you could actually do algebra with these quantities, treating them as sort of like numbers, but with a little bit of a difference because they are supposed to be numbers which are really, really small, but not quite zero. So let me give you an example of that. So we'll have a look at the previous example. So suppose you have y equals a function of x, say f of x, which is x squared over 2. Okay, so we have two variables here. There's an x and there's a y, and they're related by this functional dependence. So we can consider a change dx in x. So suppose that we're changing x by an infinitesimal amount dx. Then there will be a corresponding change in y, say dy. Okay, so how do you find this change in y? Well, it's what the function's value will be at x plus dx, this slightly new point, minus what it was at x. That's the change in y as x goes from x to x plus dx. Okay, in this particular case here, we're talking about x squared over 2. So this thing here is x plus dx squared over 2, while f of x is just x squared over 2. So we're supposed to take the difference here. Now, if you expand the numerator, you can get an x squared plus a 2 times x times dx plus a dx squared. And when you divide by 2 and cancel this thing here, the x squared terms disappear, and you'll just get x dx plus the quadratic term dx squared over 2. And now Leibniz says, okay, but wait a minute. This dx is really, really small, like a 1 over a million. No, it's actually smaller than 1 over a million, but suppose it was 1 over a million. Then 1 over a million squared is 1 over, well, it's very small. But dx is actually smaller than 1 over a million, smaller than 1 over a billion, smaller than 1 over a trillion. So this dx squared is super duper small, and we can basically ignore it. Okay, so we get x dx. This evaluates to x dx. So we get the relation that the change in y is related to the change in x in the following way, that dy equals x dx. This is the source of the term differential calculus. The calculus is about differentials. Okay, so this infinitesimal quantity is sometimes called a differential, and here is a relation between the differential of y and the differential at x. So it's a curious kind of equation because, these objects here are these strange kinds of things that we can't quite get our finger on, but nevertheless there is this relationship. Now in modern pure maths courses, people are reluctant to write this thing down kind of officially. Unofficially, yes, we use this quite a lot of times, especially when we're making changes of variables and integrals. But we prefer to sort of be on the safer side and take the quotient of these things, sort of rewrite things as saying that dy over dx is x. And then we call that the derivative of the function f that we started with. Okay. So you can see that these differentials, which are really some kind of infinitesimals, are playing a key role in both the integration theory and in the differential theory of Leibniz. And they really sort of at the heart of his thinking. And in some sense, they are continuous analogs of small changes that he understood in the discrete case. So Leibniz's infinitesimal approach, came the differential calculus, It influenced the European mathematicians greatly, and it had quite close connections with Newton's point of view too. Newton had also a kind of infinitesimal quantity called a fluxion, but he tended to think more physically. But other mathematicians came on board, the Bernoullis, notably Johann and Jacob. They were prominent exponents and utilizers of this new differential calculus. L'Hopital wrote an important book, and then Euler and Lagrange and many others made important contributions. But they all, or many of them, especially later on, they started to wrestle with some of the logical difficulties and try to find other ways, or maybe more solid ways of establish this thing. So even though there were reservations, okay, and people recognized that exactly what we're doing here is not entirely clear, okay, but nevertheless the theory was spectacularly successful, especially when it came to applications to physics and to engineering kinds of questions. So there was no question that this was a powerful thinking, and people did not want to abandon it, but they wanted to find some way of buttressing it, or bringing it into clearer focus what's really going on. In the 19th century, we had then further and newer developments, often associated with Cauchy and Weierstrass, who both sort of framed new directions for analysis and for the foundations of analysis. And these days, most people think that, sort of this attained some kind of pinnacle with Weierstrass, with the epsilon delta approach using limits, okay? And that was closely associated with infinite set theory. So infinite set theory, developed by Cantor, was then kind of used by Weierstrass to throw in these limits into the story. And that's more or less where we are today. I have a lot of reservations with this set theory point of view. I'm not a big fan of limits the way they're usually presented, but I do appreciate that these guys did really make a spectacular discovery. So there was a lot of interesting stuff going on, but I think the question of the foundational basis of the entire subject had not yet still been really understood, in my opinion. So in terms of the foundations of the subject, in the 20th century, things were more or less sort of stable as far as analysis was concerned, because people sort of started to accept the set theoretical foundations. But then in the 1960s, a very interesting new development took place, which really offered a completely new insight and actually oriented people to go back to the earlier pioneers and rethink what they were actually doing. So this is the topic of non-standard analysis, which was introduced by Laugwitz in 1965 and Robinson in 1966. And it's basically an arithmetical theory of infinitesimals, okay, which involves extending the real numbers. And you all know that I'm not a fan of real numbers at all, but anyway, so they took the real numbers and they extended it. So they actually found an arithmetical framework which actually allows these curious infinitesimal quantities, which are smaller than any positive real numbers, but still bigger than zero. And these things are called hyperreal. So they extended the real number system to something called the hyperreal number system. And this is done essentially with some logical stuff, so some techniques from modern logic, in particular things called ultrafilters, which require, let's say, flights of fancy, infinite flights of fancy, which go far beyond just the flights of fancy involved even in the real numbers. So I have a lot of problems with the foundational aspect of this, okay, but I'm happy to acknowledge that this is a very attractive theory, which explains and justifies many of the earlier calculations of the great starting analysts of the 17th and 18th centuries. So with this orientation of non-standard analysis, it was possible to go back to Leibniz and the Bernoullis and Euler and see what they were doing in a new light. In fact, to sort of justify some of the things that they were doing that at the time were questioned, and even previous to non-standard analysis was looked down upon a little bit by analysts. So it's quite interesting, and in fact it even was developed sufficiently so that there was a treatment of calculus written by Jerome Kiesler, a very nice book that shows how to teach calculus using non-standard ideas. So this has been a very important development, and it's really the closest to what we're going to be doing, because it takes the problem of infinitesimals and tries to find a solution arithmetically. Okay, so it's not having to do with variables, it's not having to do with areas and geometrical things. It's a question of looking at the arithmetic of the number line and trying to establish a richer arithmetic to the familiar one that will support these infinitesimal kinds of calculations that Leibniz, for example, was doing that I showed you. Okay, so to finish, let me point to what we're going to be developing in our next lecture. I'm going to show you the more modern algebraic, much more down-to-earth approach to infinitesimals, which it's known, but it's not widely known, and it's certainly not widely used in calculus classes. And I think it offers all kinds of interesting potential improvements to the education of young people. So basically what we're able to do is harness a lot of the insights of non-standard analysis, maybe not all of them, but a lot of them, and apply them in a very simple kind of algebraic way. So the idea is to introduce these things called dual complex numbers, and I'll explain in the next video that they essentially go back to William Clifford in the 19th century. And we're going to express them with this notation, C sub d, and let me just remind you about the framework for dihedrons. So dihedrons are the 2 by 2 matrices. Here's the basis for it. There's 1, there's I, 0, 1, minus 1, 0. I'm using that convention for negatives with a bar over it. There's the matrix J, 0, 1, 1, 0, and the matrix K, 1, 0, 0, minus 1. These 4 matrices are a basis for the space of matrices, 2 by 2, over a general field. And this is so interesting that we are now working over a general field. That's the context in which these dihedrons live. And we're going to introduce a new element, okay, called epsilon. 0, 0, 1, 0. So it's what you get when you take this one here and you subtract this one and divide by 2. Okay. And then it's easy to check that in the world of matrices, this epsilon squares to 0. So this is a quantity whose square is 0, but it is obviously not 0. And so then we can consider combinations of 1 and epsilon. For example, a times 1 plus b times epsilon, which we'll just write as a plus b epsilon. And that is just the matrix A0BA. And that is then a dual complex number. And we'll see that this gives a solid, concrete introduction to infinitesimals, completely without any philosophy, without any logical requirements of, accessing all kinds of infinite things. And very importantly, that it works over a general field, which brings into focus this possibility that we could actually do calculus over general fields if we thought in a big enough way. So this is going to play a very important role in the Algebraic Calculus 2 course, which I hope you're all aware of, which is under development. But I'm going to just explain this, this part of it further in my next lecture. So I hope you'll join me for that. I'm J Wildberger. Thanks for listening.